Alright, here's some more momentum conservation for you. This is assignment number 4 from Unit 9. Old cannons were built on wheeled carts, both to facilitate moving the cannon and allow the cannon to recoil when fired. A 150-gram cannon and cart recoils at 1.5 meters per second. What velocity would a 10-kilogram cannonball leave the cannon? Alright, so this is an explosion. Pretty obvious, I think. And everything is together at the start. So the cannon and the I'm just going to call the cannon and cart. I'm just going to call that cannon and the ball. And everything is at rest, just at 0. And then the cannonball comes exploding out of it. I'm going to say that's the forward direction. And the cannon itself recoils and it's got to have the same amount of momentum as the cannonball because I know that it started with 0 momentum, so it has to have 0 here. Okay, so it looks like the momentum of the cannon plus the ball, which is 0, is equal to the momentum of the ball plus momentum of cannon after. This is my before, this is my after. Find the velocity of the cannonball. Well, that's 0, and then the mass of the ball is 10 times its velocity is what we're trying to find. The cannon recoils. If I'm imagining the ball going in a positive direction, the cannon is going in the negative direction. So it would have, there's its mass times its recoil velocity of negative 1.5. And I'm going to do, oops, and that's supposed to be plus there, sorry. And I'm going to do a little math. 150 times 1.5 divided by 10 is 22.5 meters per second. I got a positive here because I paid attention to signs. On an icy road, a 5,000 kilogram truck rear ends a 1,200 kilogram car that had been traveling at 13 meters per second, causing the truck to slow down from 14 meters per second to 12 meters per second and the car to speed up. Okay, so I've got a car and a truck. The truck is initially going at 14 meters per second. And the car is initially going at 13. I'm going to make this smaller because the car is smaller. So I'm doing my best to qualitatively represent the fact that the truck's bigger and going to have more momentum. And then after, truck's going to slow down a little, car's going to speed up a little. So I'm just going to take one of those and move it over to the car. And again, this is a qualitative exercise, so as long as you have positive, 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 and the truck gave some to the car and they're equal number of blocks, then that is okay. And it's a collision, by the way. Alright, so in the before, I've got the momentum of the car plus the momentum of the truck is equal to the momentum of the car plus the momentum of the truck after. Again, these are not equal to each other. This is the before and this is the after. Okay, so the momentum of the car before is the mass of the car times the velocity of the car before plus the mass of the truck times the velocity of the truck before the collision is equal to the mass of the car times its speed after, which is what we're looking for, final velocity of the car, plus the mass of the truck times its final velocity. All right, I'm going to carefully do some math here. I'm going to add those up. All right, I added those together and I got 85,600. Then I'm going to subtract this. And then I'm going to divide by this, because I know how to do algebra. I get that the final velocity of the car is about 21 meters per second. If you were thinking like, okay, so the truck lost 2 meters per second, so the car should gain 2 and be going about 15. That's not true because the truck is much more massive. So the car, although it's going to have the same change in momentum, the expression of that in velocity is going to be greater because the mass of the car is smaller. If you remember back to the second assignment from this unit, I think, the Beetle and the Hummer collision. We talked about that back there. All right. During alpha decay, an atom ejects 2 photons and 2 neutrons, which is an alpha particle. When radium-226 decays, it becomes radon-222 by ejecting an alpha particle. So this is the before, and this is the after. This is an explosion. There's a typo on this. I'm sorry, it's super confusing. That should be 222 right here. Sorry. All right, so let's see what we got here. We got the radium here at the start with no momentum before the explosion. And then afterwards, I'm going to respect the directions of this here. I've got the radon and the alpha particle. Okay, conservation equation, so the momentum of the radium before, which is 0, is equal to the momentum of the radon after plus the momentum of the alpha particle after. All right, so 0 is equal to, they didn't give me a number here, but we can do like a ratio thing, I guess. And also the masses, these like atomic numbers are stand-ins for the mass, so I can use the 226, 222, and the 4. So here, the 222 times the velocity of the radon plus 4 times the velocity of the alpha particle. And we want to know how many times larger will the velocity of the alpha particle be. So I'm going to just solve that for VA. So that would be 222 over 4. So it'd be 55.5 times bigger than the velocity of that. That makes sense. This little tiny thing is going to go shooting off much faster because it has to have the same momentum and it has a much smaller mass. Its MV has to be the same. What does the negative sign mean? It just means it's going the other way from this one. So There you go, 55.5 times faster. An apple falls from a tree. Complete a qualitative conservation of momentum diagram where the apple is initially attached to the tree and the final situation is just before the apple hits the ground. All right. So what kind of event is this? I guess we're talking about the Earth and the apple being attracted toward each other, and they're not really. I think this is a neither. So I think this question is getting us to think about the Newton's third law, attraction of all things. That like with this, when this apple is falling toward the Earth is also attracted to the apple, but because the Earth is so much more massive, the Earth like doesn't notice that it's being attracted to the apple. Neither do we. So here I have the mass so I have the apple and the Earth, and the apple and the Earth. I think that I like the apple going in the negative direction. So initially, the apple does not have any momentum, and then if it's going in the negative direction, there, initially the Earth doesn't have any, so then the Earth would have to have momentum toward the apple? What? Well, yes, but the amount of momentum the Earth is going to acquire in that little interaction is so tiny because the mass of the Earth is so big. It's completely like not measurable ever. And yeah, so the momentum conservation equation, here on this side we have 0, and then here we have the momentum of the apple plus the momentum of the Earth. Ooh, look at these fancy airplane diagrams. Airplanes maneuver on the ground by using thrust from their jets or propellers. Fully loaded 396,900 kilogram Boeing 747-400 gets a total of 1,100 kilonewtons, that's like times 10 to the third. That's times 10 to the third newtons of thrust from its jet engines. And takeoff speed depends on a number of factors like air temperature, airplane weight, airport elevation, but we'll say that it's about 170 miles an hour for one of these big airplanes. Determine the time the plane takes to go from 0 to 170 miles an hour. So this is the thrust on it. So at force balanced is equal to mass times acceleration. And we're going to have to, because we don't have the information, we're going to be ignoring air resistance, which is not super realistic because it's a big plane, big hunk of metal moving pretty fast through the air. The mass of it is 3,600. All right, so its acceleration is, push some buttons on my calculator. About 2.8 meters per second squared. And if we want to know the time, that it takes to do that, well, we need to have this 170 miles an hour. Let me do a little. Let's see. Do it here. 170 miles per hour. There's 1,600 meters in a mile. Oops, dang it, I did that the wrong way around. That should be 600 meters and 1 mile. I knew that it was the wrong way around because I looked at that. I was like, that's not going to cancel out. I need the mile down here. So that's good. And then 1 hour is 3,600 seconds. So I'm going to run that through my calculator. About 76 meters per second. So I could do a kinematics problem now where I've got my acceleration is equal to 2.8 meters per second squared. Initial velocity is 0. Final velocity is 76. And I want to find the time. And I'll leave it for you to try that. But our new way of doing this would be, I know that force unbalanced times time is equal to mass times change in velocity. Right, that's the impulse momentum theorem. So that means my time would be equal to mass times velocity divided by unbalanced force, right? Just dividing both sides by that so I can find the time. And run that through. Copied that wrong. That's supposed to be a 9 there. And that time is not right. Oh, I used the acceleration there instead of the change in velocity. Let me try that again. My bad. There we go. About 27 seconds. And if you've ever been on a commercial airliner, about 30 seconds to take off. That's about right. It's a little longer for this plane because it's such a big one, but it's about right. Complete a conservation of momentum diagram showing how the initially stationary airplane gets to takeoff speed. This is, it's not really a collision or an explosion. It's kind of like a protracted collision, no, like kind of a protracted explosion with the air. Like there's air and the plane separating, but I don't think I would be tempted not to call it either one. So here, the plane and the other thing, like if the plane's getting momentum forward, there must be something that has the same momentum going backward, and that thing is the air. At the start, everybody's just chilling. Then the plane is going forward, and the air, a lot of it, is getting pushed backward. So here, no momentum. We have the momentum of the plane plus the momentum of the air. And the momentum of the plane at takeoff Well, the momentum of the airplane at takeoff is mass times velocity of that. It's mass times its velocity about, I call that about 3.0 times 10 to the 7th, if I'm reading that right, kilogram meters per second. There you go.